Yeah, let's pick up where we left off in the first lecture. Let me give you a short overview of what we did. Last time we considered an ordinary differential equation in RD. So what do I mean by this? I have Vt of x, which is a map from time, which is r plus, times Rd, which is position in space, to Rd, which gives you a velocity field, right? And we are interested in solving this ODE, which is dxt by dt is equal to Vt of xt, where small x naught is considered the initial condition. We want to solve this initial volume problem. Of course, it's a very classical topic. We also discussed the Picard-Lindlof theorem. Which gives kind of general conditions under which there is existence and uniqueness of solutions to this ODE. Okay, then in the generative modeling setting, what we wanted was, okay, we start with a random initial condition with a distribution, let's say a probability measure P naught, with density also we call P naught, and we want to understand what is the density of PT, right, of XT, which we call PT. Okay, then we derive the continuity equation. So the question was, what if initial x naught was random? Let's say density being P naught. Okay, so this is where we derived the continuity equation. This is described. I wouldn't say described. I would say that this implies the continuity equation. Okay, but the fact that it is described by it needs more work. We need to show uniqueness, or that implies something else, and so on, right? And that gives back the trajectory and so on, right? So we haven't done that yet, but I'll state those results. But what we showed is that PT satisfies the continuity equation. That is, if PT of x is the density of xt, then plus the following partial differential equation is satisfied. Divergence x of Vt of x, Pt of x must be equal to 0. So this is basically a statement of mass conservation in physics. This is very famous. Professor Borkar told me later that it's also called the Liouville equation, but we'll refer to it as the continuity equation in this set of lectures. Okay, so now let's think about some more things about this. I'll just state some fundamental results about this. So what we showed that was, if this was just a consequence of fundamental theorem of calculus along with some integration by parts. That's what we used to show this. And we want to know, okay, is this a sufficient description of the flow, right? Can this be solved, and so on. Okay, there are many things which can be demonstrated. I don't want to state these too rigorously, but it can be made more rigorous with an exact statement with all the conditions required. One is under sufficient smoothness and decay for Vt, the solution to the continuity equation given P naught is unique. Okay, what do I mean by smoothness of Vt? It means that it should be sufficiently differentiable, it should be Lipschitz, maybe uniformly Lipschitz, and so on. What do I mean by decay? It should not explode too fast near infinity, right? And all those things only make sense when you look at it with the family of probability distributions you're proposing. But there are certain ways you think about it. We can think of decay as boundedness for now. It's uniformly bounded and Lipschitz, there is a unique solution. So given an initial P naught, right? It's not like this can describe two different probability density evolutions, right, under sufficient regularity. Okay, the second thing is that suppose we start with continuity equation. we started with the ODE last time and derived the continuity equation. Okay, and okay, which is okay, and assume sufficiently nice behaved velocity field. Okay, this implies the system dxt by dt is equal to vt of xt such that x naught is distributed as p naught can be solved almost surely. And xt is distributed as pt. So this we should understand as a converse to the result. So what did we do here? We started out with this ODE, which says, okay, I go through this velocity field. What happens to the density evolution? It evolves as the continuity equation. What I'm saying is, okay, suppose I have a sequence of probability distributions and a velocity field. I tell you that it satisfies the continuity equation. Okay, then is it related? Actually, can we get back the ODE system from this? It turns out yes, in the sense that if the velocity field is sufficiently nice, for now we think of it as bounded Lipschitz velocity field. Then this is solvable almost surely whenever you start with the same initial condition P naught. And we can also be sure that xt is distributed as pt, right? So this is kind of a two-way street between continuity equation and the solution to the system of. Correct. So there, I think the objective is different. You're given some ODE from a scientific literature, and you want to have a neural network understand its solution, or rather just give you the solution once, give you the coefficients, for example, of a PDE. Here it's that we want to parameterize we want to find an ODE which fits our purpose. Discretization we will do with numerical methods ourselves. So we want to fit a neural network to this, not to the solution of this equation. So it's like, yeah, it's not that we want to solve a PDE, it's that we are trying to solve it to do something else, kind of. Oh yeah, actually yes. Now that I think of it, there are some papers which do diffusion in the function spaces, right? You can think of Gaussian processes as the noise we add in diffusion, right? So you can also noise functions just like you noise vectors, and you end up with a random function and you start and denoise, and you end up with a solution to a PDE. So given the thing, so just like I said, text to image models, it's you have coefficient to solution of a PDE model, and you start with noise and denoise it to the solution of the PDE. Those kind of works also exist. I'm not very aware of those nitty gritty details of those, but I can point you to some. So, okay. So actually these results are even deeper. It turns out that the continuity equation actually says a lot about the Wasserstein geometry of the probability distributions. We can actually consider a space called P2 of RD. Okay. This is the set of all probability measures with finite second moments. Okay. So now we can think of curves in this space. Okay, we parameterize curves. That is, mu t is a function from 0, 1, let's say, or 0, t to rd. Okay. So and we can also have a metric here called the Wasserstein 2 metric. How many of you know what a Wasserstein metric is? Okay, so a lot of you know. I won't go into the details of what to say here, and have the Wasserstein metric on this space. Yeah, on P2 of RD. Huh? Yeah, sorry, P2 of RD. Yeah, you're very right. Yes. Does not. Okay, we think of it with the topology of the WT metric. Okay, we can indeed show that W2 is a metric on the space and so on. Okay, assume that T goes to mu T is absolutely continuous. Do you know what an absolutely continuous curve is? Okay, if not, I encourage you to look it up. It actually is kind of the more stringent condition of continuity than uniform continuity. I hope most people know what uniform continuity is. Absolutely continuous means that, okay, if you're given a metric, if you have mu t minus mu s, this is less than or equal to integral some beta of gamma d gamma from t to s for some beta belongs to an L1 function of R plus. Right, this should hold for every T and S. Right, so this implies uniform continuity, but absolute continuity actually is much more helpful than this. Okay, now suppose that we have a curve of probability distributions which is absolutely continuous in the Wasserstein 2 metric, which by the way involves a lot of probability distributions, a lot of paths in the space of probability distributions. Okay, now what this implies is that the theorem, which is a very strong theorem, which I'll write here, is that there exists a velocity field Vt from Vt of x from R plus times Rd to Rd, okay, such that Vt belongs to L2 of mu t almost everywhere t, such that dou by dou t of Pt of x plus divergence of Pt Vt is equal to 0. Okay, so this is a very profound theorem. Let's take a bit to understand why this is. This won't be very relevant to generative modeling, but I just wanted to say that continuity equation is very, very important because of these kind of purposes. So I did not assume anything about how I got the curve in the space of probability distributions, except that it is very continuous. As in, it's continuous in the sense of Wasserstein distance. It doesn't, mass just doesn't disappear and go off somewhere to infinity or something very far away. Okay, so now, but then I also had this class of equations called the continuity equation, which describe the evolution of probability density along an ODE, right? So, but what this is saying is that give me any kind of a continuous curve, which is sufficiently continuous, then it has to satisfy the continuity equation. So in some sense, this is the prototypical or the most important kind of dynamics on the space of probability distributions. Right, so you don't have, this is very, very general, and you don't have to go to some kind of a nonlinear PDE or something, unless you want something very, very fancy, right? This is all the kind. This is sufficient to consider this class of solutions or this class of evolutions. Okay. So, okay, but there is another caveat here. Just because it satisfies this does not mean that we can go back and solve dxt by dt is equal to vt of xt. That's a very different question. It's just a general existence theorem. The proof of this is based on Rees representation theorem. If the probability path is not too nice, then you won't be able to solve that ODE system, right? But it will still satisfy the continuity equation in the sense of distribution, which I described yesterday, if you remember that. Okay. Okay. So now we can continue on with the important topics for, yeah. Yeah, so there exists some beta, yeah. Yeah, it's for all SNT. Yeah. Sorry? Almost everywhere. So it doesn't have to be satisfied for every T, but it will be satisfied for almost every T. Okay. With respect to the Lebesgue measure, of course. Okay, so. Yeah, so usually a lot of things have when you define things in terms of distribution, you cannot show that it holds all everywhere. You'll have to end up showing that it holds almost everywhere. And yeah, that's in the sense it works. Okay, so now we can continue off to the main topic of this session, which is stochastic differential equations. Okay, how many of you studied stochastic differential equations or even just Brownian motion? Okay, how many of you know what a filtration is? Okay, fairly large number of people. So I'll try to give an explanation which makes sense for those who don't know and those who know as well. So we are concerned with making sense of the following. So we have something, we had an ODE which could be written as V of t comma xt dt. This was what we solved. But then now we add a very rough noise which kind of tries to model the unpredictability of the system, which is sigma of t comma xt times dbt. Okay, I'm purposefully not writing this as dx by dt because this dbt need not be differentiable. It's a very rough path. It probably Holder continuous. I mean, it is Holder continuous, but it is not differentiable anywhere. Okay, this is called the Brownian motion. Okay, so this is so original works on diffusion models actually consider stochastic differential equations like this to sample from our thing. There's of course Langevin algorithm, Langevin dynamics, and so on, which is popular in MCMC, uses stochastic differential equations like this. So let's think about how to make sense of this, right? So to make sense of this, we need to understand what Brownian motion means, right? So Brownian motion is okay. So usually in more applied fields like physics or electrical engineering, people consider dBt by dt and call this the white noise. Okay, it's actually hard to interpret what this means because it is supposed to be such that let's call this zeta t is the white noise. It has some properties like this. Expectation of zeta t zeta s is equal to Dirac delta of t minus s. Okay, so we don't know what this random variable actually means, right? So this was actually kind of started off with Brown's observation on Brownian motion, where Poland particles move when you put it in a fluid, right? It has a very kind of path like this, which is very discontinuous. You cannot clearly see this as a solution of an ODE or something, but it has some randomness in it, right? Which cannot be modeled very easily at the molecular level, right? So they wanted to model this, and they added this kind of a white noise and tried to understand what this means to solve it. And then it was a person called Bachelier, I don't know, in the 1910s, I think, he came up with using, huh? Yeah, before 1910, yeah. Yeah, around 1900s, yeah, somewhere. So in some decade around that, I can tell you the exact reference maybe later. He came up with the Brownian concept of Brownian motion. He said, okay, if this kind of quantity exists, then it can be used to model uncertainty in finance, for example, right? And it was quite good, but it was hard to actually define this in a probability space, right? I'll tell you what was exactly the challenge. And then physicists and finance folks and everyone who wanted to model things used it successfully, but mathematicians were not able to define it. So it was until Norbert Wiener was able to define it in a rigorous way and tell us what it exactly means, right? And then it was actually a breakthrough, and then everybody in probability theory was very excited about this built on top of this. And then we had Ito, who rigorously studied stochastic differential equations of this sort and came up with the eponymous Ito's integral, what is now called Ito's integral. This is like fundamental theorem of calculus, but for this kind of stochastic differential equations. So right. So let's go through a very quick overview of these things. So first, let me define Brownian motion. Okay. So Brownian motion is a random function. Till now we were looking at random vectors, but this is a random function. So what does it mean? You have bt to bt. Okay, so let's say omega is the random component. This itself is a function from r plus to rd. So when I say an instance of a Brownian motion, I mean the entire function of time. So for example, one random realization of a Brownian motion could look like this. Okay, and a second realization of Brownian motion could look like this. Okay, what I mean by the Brownian motion is this entire trajectory, right? And a realization of the Brownian motion is this entire trajectory. Okay, so but there could be multiple possibilities of this trajectory. Of course, these kind of function spaces are infinite dimensional, and there are problems with defining probability measures on an infinite dimensional space, right? Actually, so there, we know that we can define countably infinite number of independent random variables, right? Do you know what problems we run into when we try to define uncountably infinite number of independent random variables? Correct. So it's more like Radon-Nikodym theorem fails. You cannot even do conditional probability in those kind of spaces. So you have to restrict yourself to kind of Polish spaces, which are more, there is some kind of separable, it's a separable topology. Right? So therefore, okay, probability theory hinges on conditional probability and so on. And Radon-Nikodym theorem is how you arrive at conditional probability. If that doesn't hold, you can't do probability theory. I mean, you can define those and study those, but you can't do probability theory like we understand it. Okay, so very importantly, this had to be defined with countably infinite number of random variables, independent random variables. So that was the problem with this. Okay, so okay, let's try to see what kind of properties we want in the Brownian motion. Okay, first one, b0 is equal to 0 almost surely. Okay, so b0 is a random variable. Okay, at each time it's a random variable. We want it to be 0. Okay, then for t greater than or equal to s, bt minus bs is independent of bs. Actually, we can actually make it for all tau less than or equal to s. Okay, so that is the increment you saw after time s is independent of everything that happened in the past, right? The third thing is bt minus bs is distributed as standard normal distribution of t minus s times identity. Okay, so and the fourth one is that t goes to bt. This is a function which of a single realization is continuous almost surely. Okay, right. So now we can we want to construct such a thing. Let me ask you a simple question. We have this 0.3. Can you use this 0.3 to tell me what is the order of magnitude of bt minus bs when t and s are close to each other? Order of magnitude. Let's say t minus s is like epsilon. What is the order of magnitude of bt minus bs? Correct. It should be of the order square root t minus s, right? So now let's ask the question. Okay, so if bt was a differentiable function, it's a Lipschitz function, then what is the order of magnitude you would see of bt minus bs? Correct. It's of the order t minus s if it's a Lipschitz constant 1, right? So that's why we have this. So it cannot be Lipschitz. It's much worse than Lipschitz. It grows much faster locally than Lipschitz, right? So this is the source of all our problems. Why we need to have the Ito theory of integration, right? Okay. So let me get back to here. Okay. So now I showed you. I mean, how to construct this is a very nice theory. Actually, you can construct a probability over a Hilbert space, and then you project it back to RD. I would actually recommend that you look it up. It's actually, we construct a probability distribution over L2 of R plus, that is the set of all continuous functions from R plus to Rd, and then it's a Hilbert space, and then we use a countably infinite number of Gaussians to construct an isometry to that and construct it. And then use something called the Kolmogorov continuity theorem. This is all very, very interesting from a function analysis perspective. I probably don't have the time to actually cover these aspects in these lectures, but please do look up in, let's say, Legol's book or something. There are many treatises on stochastic calculus. Any one of them should be fine. Okay. What I'm concerned with now is interpreting and solving the stochastic differential equation, which gives us Ito's, which brings us to Ito's theory, right? So I told you about something like dxt is equal to v of t comma xt dt plus sigma of t comma xt dbt. Okay, so I told you that dbt by dt does not make any sense. Like I said, if it was a differentiable function, it would grow locally as t minus s, right? But it grows as square root of t minus s, so it explodes if you try divide it by dt, right? So its derivative doesn't exist. So how do we make sense of this? Does anyone have a idea? How do we make sense of a stochastic differential equation? Sorry? Correct. So the idea is to actually not try to solve a differential equation, it's to solve an integral equation. Okay, it turns out that integration, you can perform integration on a much larger class of functions, much less well-behaved functions than differentiate them. So let's actually try to solve the integral equation. So we want to solve the following integral equation on random trajectories xt such that given a Brownian motion, this holds for all t almost surely, right? Xt, just like dbt, xt is also a random trajectory, which is a function of, let's say, hopefully of this Brownian motion. I'm given a Brownian motion, which is a kind of a driving, disturbing noise, and then and then I kind of try to solve this integral equation, which is solved for all t almost surely, right? So this is what I want to do. So I kind of know how to do this integration. If I'm given a trajectory, I can do this. If v is continuous, I can do this, right? So, but what about this? What does this actually mean? Right? So that is the Ito's calculus part, right? To be able to interpret what this integration means, we can actually solve this SDE. So there are many theories of this integration. Two most famous ones are Ito's integral and Stratonovich integral. And why are there two different theories of integral? Because it's not clear how to actually define this integral in a correct sense. I'll tell you what is the problem if you go with standard Riemann style integration theory and try to interpret this function, right? So okay, so let's actually delve into that. So there are two theories. There is Ito integral, which uses martingale method to construct these integrals, and there is, of course, Stratonovich integral. This one uses some kind of a midpoint. It is much harder to analyze, but it could make more physical sense in modeling some actual physical systems. But we will be mostly dealing with Ito integral. Okay, so okay, so let's actually look at why this is hard. The first thing is we attempt to define it using Riemann styles integral. Okay, how many of you know what a Riemann styles integral is? Okay, fair number of you know, but let me give a quick primer to those who are not aware of this. Okay, so given two functions of time, let's say f and g, let's say they go from 0 to t to, let's say, rd, or you can just consider it to be r. It won't make much difference. Let's for now just say r. Okay, so now we want to make sense of integral f of t dg of t 0 to t if you are in 12th standard, you kind of use this kind of differential forms and try to integrate it and so on. You change the variables. But how this is actually defined is, okay, is you can, for example, take summation over delta f of summation over I f of ti times g of ti plus 1 minus g of ti, okay? And you can take limit as, ti minus ti plus 1, the grid size tends to 0. Okay, this is how you define Riemann integration if you remember your course. So basically you take the set of all times I equals 1 to n, you take n tends to infinity so that the grid size tends to 0, and if this limit exists, then it is defined to be the integral. Now instead of ti plus 1 minus ti, I wrote g of ti plus 1 minus g of ti. Okay, so this converges under certain conditions. So under what condition does it converge? Okay, converges to a limit, okay, when f is continuous and g has finite variation. Okay, does everyone know what a finite variation function is? Who doesn't know it? I'm happy to explain. Okay, finite variation function, let's think of it as Lipschitz function. Okay, so it's supposed to be like summation I g of ti plus 1 minus g of ti. Okay, if you have an increasing sequence of times and you sum this up, okay, this supremum over all such grids should be less than infinity. Okay, Lipschitz continuous function, for example, would be a finite variation function, right? Why is that coming in? Because we don't want this quantity to blow up, right? So that's why we have a finite variation function. Okay, so this converges to a limit when you have f is continuous and g has finite variation. There's also another condition when you can actually show that this exists, and it exactly like is the theme in all these lectures. It involves integration by parts, right? You can actually see that it converges when f is finite variation and g is continuous. Can anyone tell me why that would be true? Okay, I told you the answer. Okay, so we can actually define this as integral 0 to t f of t d g of t. We know we can have it to be capital F of t, g of t minus f of 0, g of 0 minus integral g of t df of t, and we can show that this this relation can actually be extended to a definition of this whole integral, right? So we can define this Riemann styles integral for when f is continuous and g has finite variation, when g is continuous, when f has finite variation, right? So now let's see what goes wrong when we try to attempt to use it with our Brownian motion type integral. Okay, so with Brownian motion it will be, let's say we just want to integrate something like integral bt times dbt. Okay, we know bt is continuous, right? Because that's one of the axioms. By construction, it is continuous, the existence theorem. Okay, so but it does not have finite variation in any interval. So the problem is bt does not have finite variation anywhere. Okay, so you can't extend this theory to apply to this kind of an integration. So,
but here we wanted sigma times dbt. So why couldn't I do the switch it like?
Okay, so you would expect that if I have a function sigma of t comma xt, sigma is let's say xt, and it's a solution of this, it would locally be like
I
very
see.
buzzy,
Okay.
right? So you want to integrate
It's,
something which is not finite variation. So, I mean, this is just an example. We can think of other things. Right? So yeah, so integral bt dbt doesn't have finite variation anywhere in any interval, so we cannot kind of integrate this. Okay, so that's where Ito's idea came up. So we can okay, it's actually very hard to actually define these integrals point to point. That is, I'll give you a bt, and then can you make sense of this integral? It may not be actually be possible. Okay, actually integrating these things is called, there's much more recent development, much after from the 90s, called rough paths theory, as to show how it exists path by path. And I don't know much about rough paths theory, but it's been used to make sense of Kardar-Parisi-Zhang equations and so on. And I think Martin Herer won the Fields Medal for doing that kind of theory. But we'll go back to the probability theory sense of understanding this integral, which is that in the L2 sense. We will not be defining these integrals for every path. We'll be defining this as a random variable. It converges to it in L2. But if you tell me what is the value of this at this omega, I won't be able to tell you, right? So that is sufficient for our purposes to solve this kind of an SDE. Okay. Okay. So now actually let's try to look at this Stiles integral. Will be inspired by this. So what Ito's integral does is that we want to integrate a function. Let's say we have a filtration ft, which is sigma of bs such that 0 less than or equal to s less than or equal to t. This is called a filtration of the Brownian motion. That is, it will contain all the information of the Brownian motion until time t, right? And then we have zeta t, which is, for now, let's say, is continuous. So t to zeta t, this is also a random process, right? Is continuous almost surely and adapted to the filtration. Okay, so what I mean by adapted to the filtration is that this zeta t is measurable with respect to ft. For example, in this example, we had, okay, where is this? Bt is by trivially adapted to the filtration ft, right? So we are integrating things like that. If you believe that xt, this solves the integral equation, right? So then xt can be written as a function of x naught and all the Brownian increments until time t. So xt belongs to sigma, is adapted to the filtration through this thing. So sigma of xt is adapted to the filtration. So that's the process zeta t we are trying to look here. If you have any questions, I'm happy to clarify this. This is a bit of a subtle point, but which might need more explanation. Yeah. Do you know what a sigma algebra is? Okay. So do you know what sigma algebra of a random variable is? Correct. Yeah. So it's a set of all, it's a sigma algebra of all the, yeah, correct, in this measurable space. So now you take take all the finitely many marginals of the Brownian motion, let's say bt1, bt2 to btn, such that they all lie between 0 and s, 0 and t. Okay, you can consider all the sigma algebras of all of these, right? And take a union and complete it. That's what this quantity is, right? So that is the sigma algebra of all this. Actually, this continuity assumption is not required. We need something called progressively measurable, but let's deal with continuity for now. We won't make it too hard for now. Okay, so now if this holds, we can actually extend the Stiles integral to the stochastic case, which I'll continue over there. Okay, so now we can actually show that integral 0 to t, we want to do this. Okay, zeta t dbt, we want to define this as some kind of a limit such that tn minus 1 converges to 0, swoop over, and summation I equals 1 to some capital N zeta ti times b ti plus 1 minus b ti, right? So same way as the Stiles integral. So we want to note something. First is that this is the initial point, and this is an increment. It is a future increment. right? It is BTI plus 1 minus BTI. So this increment is independent of BTI. Why? Because of our assumption 2 here. That is, any Brownian increment is independent of the past, right? So BTI plus 1 minus BTI is independent of BTI, and zeta Ti is measurable with respect to the past. So this increment is independent of this. Okay. So now what can you say about the expectation of this quantity? Huh? Yes, it is 0. Why? Because this is independent of this, and this has 0 mean. So this has 0 expectation. So this actually leads to something called a martingale, right? If I have a partial summation over this, this leads to a martingale, right? And you can actually use a lot of original Litos papers had to do a lot of computations to prove this, but then Doob came up with his martingale theory and something called Doob's maximal inequality, which simplified the setting. Okay. Actually, there is one thing missing here. One is that I've defined this to be the limit of something. Okay. In what way are we taking this limit? There are many ways to take a limit of a random variable. There is an almost sure limit, there's an L2 limit. So what is this limit which makes sense here? Exactly. So actually, we cannot define this in an almost sure limit, because I told you that these are rough paths. That would mean that you can integrate these kind of functions almost surely. But these exist in L2, right? Which L2, if you have studied basic probability theory, you would know that L2 convergence and almost sure convergence do not imply each other. You can have something converging in L2, but it need not converge in almost surely. You can have something converging almost surely, but it need not converge in L2. So this convergence is in L2. Soup or rather soup over n. So you have time, this 0 to t, and then you have t1, t2, t3, and so on, and tn and tn plus 1. I mean that this grid size should go to 0. Okay. So by using martingale methods, we can show that there's a limit in L2 of the probability space. Okay, and that is called the Ito integral, right? This limit okay. So we have this answer, right? So now we know what an integral means. Okay, for a yeah, omega is the underlying probability space. So it has to be seen as a function on the probability space, which gives me some image over RD, for example. Okay, so how do we think about this? We think about this is that, okay, this, if I just give you a path and ask you to integrate, it doesn't make sense. But if I give you some random path with very high probability, typically it will cancel out all this weird behavior, and then you get a number, which actually makes sense. That's how we should think of it as. Okay, so that's why we talk about something called finite variation, but this has finite quadratic variation. Okay, so that is the difference between ODE and SDE. SDEs, you typically deal with something with a finite quadratic variation versus something with a finite variation. So, okay. So, I mean, there's a lot to be said here. I'm just giving you some intuition as to what style of results hold in this kind of a case. It's all right. You can ask me more questions, clarifying questions if something is unclear. I'm happy to explain more or give you more references to where you can understand this in a more rigorous way. Yes, correct. So as you can see, if you make a small error, this Brownian motion moves by root alpha, right? If you t minus s is alpha, it moves by root alpha. In ODE, it moves by just alpha. You accumulate quadratically more error. Let's think about existence and uniqueness of the solution, right? This was developed mostly in the 50s and so on. And Ito was one of the earliest people who thought about these kind of questions. Okay. Okay. So let's for now think of the simplest case. These are, the velocity field v of t comma x is a function from r plus times rd to rd. Can someone tell me what the dimensions of sigma should be? It need not be a number. What can it be most generally? It's a matrix. It can be a matrix. You think of it as a square root of a covariance matrix, right? So locally, we have identity increments here. So this is n of 0 comma identity, but you can change the covariance matrix to whatever you want. That's why we have that covariance term there. Okay, so we want, and we have sigma of t comma x is a function from r plus times rd because it's a function of space and time, and this should go to rd by d, which is any set of matrices. Okay. Yeah. Yeah, it's general, it's fine. Yeah, it can go to any PS, it can go to the PSD space. That should be sufficient. Dimension of? Oh, yeah, correct. Yeah, that is true. It could be D by D prime. So that would still give you a different thing. Yeah. So you can reduce it to a case where it can be because it only depends on sigma transpose. Okay. So okay. In this setting, we consider this velocity drift and the diffusion coefficients to be uniformly Lipschitz in space. That is, x goes to v of t comma x for every fixed t is a Lipschitz function, and it is uniformly continuous in time. That is, t goes to v of t comma x is continuous. Okay. Okay. So this is our setting. Okay. Sorry, v. Okay. Yeah. Okay. So in this setting, we want to show. Yeah. Yeah. These are the assumptions. Yes. Okay. So actually, these are the assumptions because I haven't told you what a strong solution is. Okay. So what we are looking for is a strong solution. Actually, there are many nuances in what it means to have a solution to an SDE. So there's a concept called weak solution. There's a concept called strong solution, and you need not actually be able to solve something as a strong solution. But let's actually attempt to obtain strong solution. All the SDEs we consider in this are simple, and they actually have strong solutions. Okay. So what is a strong solution? There exists, given a Brownian motion, Bt, okay, then there exists xt, t goes to xt, a random function such that this satisfies xt is equal to integral p of t comma xt dt plus integral sigma of t comma xt dbt. And the second point is xt is measurable with respect to sigma of bs such that s less than or equal to t less than or equal to 0. It's adapted to the filtration of the Brownian motion, right? So this is what we call a strong solution. Okay, so I mean, this is good enough for our purposes. When what do we call a weak solution? We say that we are not given a Brownian motion. We'll construct a Brownian motion, xt and Brownian motion such that this holds. but this need not be true. Right? There's a subtle nuance there, and there is something called Tanaka's equation, which actually doesn't have a strong solution but has a weak solution, and which is kind of beyond the scope of this set of lectures. But I would actually implore you to look it up if you are interested in these aspects. Yeah. So no, it's more like you give me a Brownian motion and I'll give you an adapted solution. But weak solution is that I'll give you a trajectory and a Brownian motion such that this holds. But I cannot give you a solution to the given Brownian motion. Right? No. There exists a map. Sorry? Yeah, you're right. Yeah, this is actually too much of T. Actually, I think I've done that mistake even there. Is that an S or a T there? Yeah, I think that's a mistake here too. Again, this is not a, let's use a dummy random variable here. Let's call it an S. Okay. So it's an integration variable, which makes this imprecise. Let me actually write this down again. Oh, yeah. Correct. Yeah, you're right. Here, pairwise should hold. Yeah, it has to be for all things. Yes. That is a very important subtle point. Yeah, which sigma algebra of this. Correct. Yeah. Joint independence. Yes. So yeah, right. It's a sigma algebra of all these things. Okay. Any finitely many things from the sigma algebra. Yeah. Individual guys. I mean, it's actually the first thing you learn in the theory of independence is that pairwise independence does not imply independence across. Okay, so what do we call a strong solution in this case? So there exists a random map, okay, which is, let's say, t goes to xt, okay, which satisfies the following integral equation, which is v of s comma xs ds plus integral sigma of s comma xs dbs. Okay, well, what I'm saying is there's a trajectory xt such that this integral equation is satisfied. Okay, and the second thing is that xt is sigma belongs to the sigma algebra of bs such that s less than or equal to t. So this is what we call a strong solution to a Brownian motion. Of course, we are given an initial condition x naught is equal to, let's say, some x naught. Okay, this is a minor point, but yeah, this is what we mean by a strong solution. Okay, under let's say this is a setting A. Okay, the theorem is under setting A, there exists a unique strong solution. Okay, what I mean by unique, there needs to be an asterisk. It's called pathwise uniqueness. That is, if there are two solutions, they are indistinguishable almost surely for every t. That's the notion of uniqueness. It's a subtle point which is not really important for us. So I'll put it in an asterisk here. There exists a unique strong solution to. It also is continuous. Yeah. So right. So we have the following existence theorem. So right. So now we need to derive something called the Ito's formula. We now understand that we can solve these integral equations, and now how can we do kind of Taylor series kind of approximations with this, right? So like we derived the continuity equation using Taylor series and integration by parts. We need the version of Taylor series for these kind of increments, which are non-differentiable increments. So that's where Ito's formula comes in. Okay. So now suppose we have solved okay, xt is equal to integral v of s comma xs ds from 0 to t plus integral from 0 to t sigma of s comma xs dbs. Okay. So now last time what did we do? We saw how it for a test function phi, how did it change the value along this trajectory? Okay. We will actually do that here. Okay. So we consider phi of t plus epsilon comma xt plus epsilon. Just like last time, we take phi to be an element of cc infinity of, let's say 0 comma t times rd. This time, this need not be an open set. Okay, this can be a closed set. So it need not vanish at the endpoints of time, but it has to vanish at the endpoints of space. Okay. Okay, so let's see how this evolves, phi of t comma xt. Okay, so what is the problem with just using Taylor series approximation to get an answer here? No, CC infinity is infinitely differentiable, right? You can apply, so I'll just give you t plus epsilon and xt plus epsilon and xt. First, let's say we truncate it to first order Taylor approximation. Yeah. Sorry? Correct. So, composition of, no, but you can use differentiability on this. Suppose, okay, what I'm saying is you can take this and you can do something like dou by dou t of phi of t comma xt times epsilon plus, let's say, gradient phi of t comma xt times xt plus epsilon minus xt. Why is this not good enough? Yeah, sorry. No, I'll just give you xt and xt plus epsilon. Why is this not a good enough? Okay, usually in ODE, we would just like so plus higher order terms. Correct. The higher order terms need not be epsilon squared. Yeah. Let's take a closed set this time. It was important that it was open set for the continuity equation, but because we wanted it to vanish at the both endpoints, we don't want to it doesn't have to vanish here in our case for Ito's formula. Finally Fokker-Planck equation requires that, but Ito's formula doesn't. It's a strict subset of this, so it should be. Yeah, so, right, so this is not true. Why? Because Brownian motion locally increases as root epsilon. So there are some second order terms which will actually matter for us, right? So, okay, let's actually see for that, let's unpack this xt plus epsilon minus xt. This is approximately equal to v of t comma xt times epsilon, okay, plus we have something like sigma of t comma xt times, b of t plus epsilon minus bt, right? So why didn't I consider a midpoint here? It is very important that I not consider the midpoint here, we're hoping that it is better, because that's how Ito integral is defined. If we consider the midpoint, it converges to something called Stratonovich integral, and it gives you a completely different answer, right? Because we are using Ito integral, Ito's formula has this form, Stratonovich integral has a very different form of this kind of equations. Okay, yeah. Yeah, because of, okay, where did I explain this? Yeah, here. Right, we go here, right? Why was this zero mean? Because we considered the initial point here and the future increment here. But if you took the time ti plus 1 plus ti over 2, this is not zero mean anymore. Correct. It converges to something, but it converges to a different random variable, which need not have a zero mean, for example. Correct, not in the future. So that leads to something called a Stratonovich integral, right? So it gives you a very different result, yeah. Yeah. So if there was any unambiguous theory like the Riemann integral, this would not have happened. This only exists because of very weird fluctuations in the Brownian motion probability distribution. Okay, so I will argue that because we are using Ito integral, this is a good enough truncation. Okay, okay. So now this is fine. This is fine. Let's see what the second order term is here. This would be, this would involve a Hessian. This is plus xt plus epsilon minus xt times Hessian at t comma xt times xt plus epsilon minus xt times 1 over 2. Okay. So this is this, and take me at my word that everything other small larger than this is small o of epsilon. That we can ignore it because bt plus epsilon minus bt is of the order small o of root epsilon or order of root epsilon. Okay, so now let's actually unpack this. If we actually write this out, I'll actually use this as an exercise for you folks. This is equal to dou by dou t, p of t comma xt times epsilon plus gradient of phi times epsilon times v of t comma xt plus gradient of phi of t comma xt times sigma of t comma xt times bt plus epsilon minus bt plus half bt plus epsilon minus bt transpose times sigma transpose gradient of phi times sigma times bt plus epsilon minus bt plus small o of epsilon. The rest of them are lower order terms. Okay, so let's unpack each of these terms. The first one is because the function itself is changing over time. The second one is because of the drift plus this Brownian motion random fluctuations. The next higher order term is because of the quadratic variation, finite quadratic variation of the Brownian motion. Okay, this is called the quadratic variation term. That's why this picks up a Hessian term. So it actually depends on the curvature of the function at that point, not just the derivative slope and how the rate of change of a function along this trajectory. Okay, now this is the next step. This is the first step, the Taylor approximation, and okay, next step is we'll sum over all of these t's. Okay, so summation over I equals 1 to, so phi of capital T comma xt minus phi of 0 comma let's say x0. Okay, we can write this approximately as summation I equals 1 to let's say n phi of ti comma xti minus actually this is exactly equal phi of ti minus 1 comma x ti minus 1. Okay, this is just a discretization of the grid where each of these are small. Let's think of this as this is t0 and this is tn. Okay, this is t1, t2, and so on, such that each are epsilon at epsilon distance of each other. So we can we kind of write it as such that ti plus 1 minus ti is let's say epsilon. Okay, so then we know by our formula that this is approximately equal to epsilon times summation I phi of I equals 0 to n minus 1 phi of ti minus 1 ti comma xti plus epsilon times grad phi of comma v of ti comma xti plus grad phi comma b ti plus 1 minus bti. Let's call this subscript plus summation over I b ti plus 1 minus bti transpose sigma transpose okay. So plus small o of epsilon times n. This will converge to 0 as we take epsilon tends to 0 and capital T is finite. Okay. So now we can see that what these parts converge to. How much longer do I have in terms of time? 5 minutes. Okay. Okay. So we are almost out of time. Let me just derive the ethos formula for now, and you can take me at my word for it that I've read Legol's book on this. It is actually true. Which one? Where is an epsilon? Yeah. Correct. It is equal to big T. Small o. Yeah. It converges to 0. Okay. So this part can be written as an integral as epsilon tends to 0. We can have a rigorous argument later, but this is actually equal to dou by dou t p of t comma xt plus this actually converges to this quantity plus integral grad phi of t comma xt times v of t comma xt dt. So this is what we saw in the continuity equation. When we didn't have the Brownian motion, when sigma was 0, this was all we got when we looked at how rate of change of these functions. Okay. But due to Brownian motion, now we have two terms. Okay. This second one is integral grad phi of t comma xt times dbt. This is the Ito stochastic integral. Yeah. Is there no, it's not here. It's not here. Because xt plus epsilon minus xt is equal to this. There is an epsilon here, but no epsilon here. Yeah. It's a Brownian increment is the root epsilon, which you show. Okay. So now the third term which we had was this was the limit of epsilon tending to 0 of 1 over 2 summation I equals 1 to n, or I equal to 0 to n minus 1 of bti plus 1 minus bti times sigma transpose sigma I bti plus 1 minus bti. Okay, this is also a transpose. Now, actually, there's a interesting. Okay, what is the expectation of bti plus 1 minus bti transpose bti plus 1 minus bti? Sorry, this quantity. Look at the definition of the Brownian motion. What is the expectation of this quantity? Yeah, correct. Times identity. Ti plus 1 minus ti times identity. Okay. Trust me when I say this that we can use some kind of a martingale argument to show that this in fact converges to its expectation. Okay. And you can use a little bit of matrix equalities and identities involving the trace of an operator to show that this part is in fact equal to 1 over 2 summation 1 over 2 integral trace of sigma transpose p of t comma xt dt. Okay. So this actually ends up, we can actually replace this with the identity using some martingale theory arguments, and you'll actually end up with the last term being this. Okay. Let me write down in the last minute, hopefully, I'll write down the full clean version of the Ito's formula, which we can build upon in the next lecture to actually study diffusion models. Okay. So what we say is that phi of t comma xt minus phi of 0 comma x0 is equal to integral 0 to capital T dou by dou t of phi of t comma xt dt, first term, and the second term is grad phi of t of xt comma v of t comma xt dt. This is the second term, and there is a third term, which is integral 0 to t grad phi of t comma xt comma sigma of t comma xt dbt. And the fourth term, which is a second order term, which shows up because of finite quadratic variation, is integral 0 to t half trace of sigma transpose grad phi of t comma xt times dt. Okay, so this is what we call Ito's formula. I can take any more questions here, but we will actually, it's all right if this was not 100% clear. I ramped through a lot of technical points through this lecture, but hopefully, you understand the gist of what I'm saying so that we can actually apply it to diffusion processes in the next lecture and try to see how we can derive diffusion models out of this. Right? It would be much less technical henceforth. Oh, sorry, it's once. Thanks for catching. Yeah. No, sorry. Is it there both places? There's only half there. There's only one half.
No, no. Third term. Sigma dB.
Where is sigma dbt? Here. This it has to be sigma dbt, yes. Okay. Thanks for catching that as well. Yeah, here also it is a sigma dbt. I think I started the mistake here, but this one is correct. Yeah. Yeah. So those sigma dbt. Huh? No, it is there. This one. Yeah, it's there. If you can look at the final answer here, it's there in the sigma dbt. Okay. Any other questions? Oh, we didn't take any expectation. Oh, this one. We can actually show that if you take epsilon tends to 0, this converges to this quantity in L2 using some martingale arguments. I mean, it's still, yeah, it's just epsilon going to 0. It's not, I'm not taking any expectation here. So where can I find this treatment? Oh, I see. Okay. Okay. Is it possible to do it in RD? Okay. Where? Here. Yes. There should be a non-byte. Okay. Lots of typos because I try to ram through everything in 1 hour 15 minutes. But yeah, forgive me for the error. But the last formula I feel like is correct. Yeah.
If there are no further questions, we can break for lunch, and you can ask any further questions at lunch.
Yeah.
Let's thank the speaker.